Welcome to this one. So, all right, so now we're gonna shift over gears a little bit now that we've learned a touch on probabilities. This video is gonna be in the introduction to probability distributions. So we'll talk about what that distribution is. If you've studied functions in grade 11, and I'm assuming that you most likely did, because if you're gonna be doing data management and probability courses, then in grade 12, you probably had to go through grade 11 at some point. So probability distribution has a very close relationship with functions. So it actually is one. Now there's different ways. So as you know, we had X and Y's, the dependent and independent variables. So this kind of works the same way. So we'll talk about kind of random variable. So, the word variable you have seen. We've utilized X, okay, so what that variable is. Random, okay, is kind of important because it relates back to probabilities in some sense. So you can have measurable property and attributes, so that typically is the variable, so something that we can measure in some particular way, okay, and it has a single value for every outcome that might happen. Okay, now these variables can be discrete and continuous, or continuous, and you've seen that. Most of the time we study continuous, but with random variables, at least for the introduction, we pretty much confine ourselves to discrete random variables in the beginning, okay, when you're in grade 12. So another aspect that we'll try to touch base on is uniform probability distribution, which happens quite often, kind of like flipping a coin or rolling a die, assuming that the coin and the die are actually fair. And then I'll try to explain to you the expected value, okay, or sometimes known as just as the expectation. It's not really called the weighted average, but from elementary school and maybe at some point in high school, if you study weighted averages, then the expected value is kind of an equivalent thing. That's exactly what we're calculating, except the weight is the probabilities. And you know that probabilities all sum up to 1 just by definition, if everything is actually working out correctly. So let's try and dive into these topics, and that's going to be the introduction to this probability distribution that I want to cover in this video. So what is this probability distribution, right? So this is the first thing. If you are talking about probabilities, so what I'll do is I'll try to provide you a couple of examples. So let's say if you had a die and then you were rolling that die, that let's assume that it's a fair die. So you can have either a result of a 1, a 2, a 3, okay, a 4, a 5, or a 6. And, we can calculate what the probability of, let's say, getting a 1 is, right? We can calculate what the probability of getting a 2 is, and so on, all the way what the probability of getting a 6 is. Now, it turns out that all of these probabilities, okay, if you were doing an experiment, so you can do, let's say, an empirical kind of probability where you're just rolling this die, 10 times and then 20 times and then 100 times and 1,000 times, okay, and so on. And eventually, you might get to the theoretical probabilities. And that these probabilities, because of the fact that we have 6 sides, they're all equivalent, right? So they're all 1 over 6, okay? So they're uniform, okay? So that means all of them are exactly the same. Now, what is this probability distribution? When we care about one particular result, what's the probability of obtaining a 1? Let's say it's 1 over 6. That's all fine, right? But what if we wanted to see what the entire distribution for all the possible outcomes that would be, right? So that relates it back to now a probability, okay, because what are the probabilities? And then the word distribution means just how are they distributed across all the different outcomes that you have. And you can graph it exactly like you would a particular function. So, I can simply say, all right, so let's graph this whole thing out. And I'm going to put here, so here's my X and then my Y axes, right? So here I'm going to put P, okay, of X. And then let's say X, this is going to be the outcome. So 1, 2, 3, 4, 5, and 6. Those are only the possible outcomes that you can have. They are discrete, okay? So this is going to be relating it back to, for example, the variable itself. So we have a variable x. Now, we don't have to call it x, but we've just got so used to doing that, okay? We kind of continue that sense in probability distributions, and in particular, in these random variables. So the random variable, so the variable itself, okay, is related to these outcomes. So 1, 2, 3. So I graphed it in here. So those are the possible outcomes. And we do typically provide them as some kind of a number, right? Now, when you're rolling a die, then it's already a number because you're just saying, okay, so, you know, what's the probability of obtaining a 1? So the variable itself, okay, would be the actual numerical value that you get. So that's the property or the attribute. Okay, so within here, we are going to be putting in, so this is, you know, the results of the random variable. Okay, so the random variable, so for us, all right, so this big X, okay, it is made up of, so it's the domain, so this is 1, 2, 3, 4, 5, and 6. So if you were thinking of a domain, okay, and then, you know, one element, okay, we designate it with a small little x, okay, and it could be any of these, right? So that's exactly what we did in functions. And now, you know, if you want to plot the entire thing, so you want to have the distribution of the probability, so our function, instead of using f, right, we used to write f of x is equal to, and then whatever our results would be. But as you know, you can also plot these, okay, or state them in, let's say, tabular form. You don't have to always have them plotted out. But in this case, we could. And what we know is, so this is pretty simple, right? We know that they're all equivalent. So this is going to be all exactly the same. So our function right here, okay, so notice it is discontinuous, okay, in a sense, and therefore this variable is discrete, all right? So we have this as discrete because, okay, there are actually, you know, it's not a continuous flow, right? We don't have the results. The results are 1, 2, 3, 4, okay? So they're separated. There's nothing in between them, right? In here, okay, there are no results anywhere within here. So that's what makes it discrete. And if you're thinking back, okay, of the variables themselves, if they were continuous, that means we could, you know, plot a nice, very beautiful function where it was all connected. But in here, okay, this is the best that we can do. So we can see that this probability distribution, so now we can see what is the distribution across all the possible outcomes. There's only 6 of those. And that's what they are. And now sometimes you'll see them, okay, in textbooks that they'll actually graph it, you know, and they'll put almost like a bar graph, okay, if it's individual, especially for discrete points, okay, so it's not just a point, okay, that is plotted out, but you know that this is really just 1 and then 1 over 6 if you were plotting this as an actual point on an x and a y plane. All right, so now the distributions, you know that if you count all of them up, the probabilities are going to sum up to 1. So it doesn't matter how we plot these graphs, how they're distributed across, you know that the summation of them is going to be equal to 1 because that's what probabilities always sum up to. So we know that we have the summation, okay, of all the probabilities, okay, of all of these different points, okay, of x. So this is x, this is the summation of x is equal to, so it's starting from 1, all right, okay, and then it goes all the way up to 6 in our case, okay, so this would just simply be what's the probability, you know, of x1, okay, so seeing the number 1, okay, plus, you know, what's the probability of seeing 2, and then so on. Well, we know that these are all 6s all the way up, and they always equal to 1. The distribution itself is just how are they distributed. We would call this a uniform distribution. Uniform because they have exactly the same probability for every single outcome. So if that happens, then it's called uniform, that they're identical, right? They do not change in any ways, okay? So that would have been called a uniform probability distribution. And now another one, which could be simpler, right? And this is what I want to just show you with these variables. What if instead, we were flipping a coin and we either have, so a heads, okay, or we flip and of course we can have a tail. So we only have really two results. We know that the probability of seeing a heads is a half. The probability of seeing a tails is a half. All right. But now, if we wanted to do a probability distribution, okay, sure, we can do something of this nature where I'm going to do the entire thing and I can say, okay, this is a heads or a tails, right? This is my X. But we don't typically like to write, okay, our random variables. And the result of it is, okay, so the attribute, it's, what side does it fall on? So the random variable itself is, okay, what side of the coin is it? And then the outcomes would be it's either a heads or a tail, okay? But we, most of the time, will map this out into a number. So we'll say that, okay, maybe the heads will designate it as a 1, if it falls on heads. And if it's a tails, we'll designate it that it falls on a 2. But that is arbitrary. You could have said heads is 0, or heads is -1, and tails is maybe +1, right? So you can map it on because of the fact that we would like to have these as actual numbers. And the reason for that is because later on, if you're doing any calculations, you can't really multiply, heads times its probability, which is, 1/2, okay? And then it's 1/2 that way. This is meaningless, heads times 1/2. But if we assign a number like 1, then we can actually do a computation, all right? So we typically will not provide the random variables, okay, the individual elements as some kind of, a word, okay, description. It's going to be mapped onto a particular number. This was very easily done when we were dealing here with the die because, rolling and you're seeing a 1, it was already a 1. So that nicely mapped on, and then we can create the random variable, which was, what number of the die does it fall on, right? That's the random variable. And then the possible outcomes were 1, 2, 3, 4, 5, 6. Here, our random variable, okay, is what side of the coin do we obtain? And the outcome is heads or tails. But heads is not a number and tails is not a number. So we typically will assign some kind of a number, okay, for this. So in both of these cases, so this is, okay, also a discrete. So this is also discrete, okay, because of the fact that these are separated outcomes, right? There is no merging in between. Now, you might say, okay, so probability distribution, so if I go back in here, okay, that probability distribution is just how are the probabilities distributed across all the possible outcomes that you might obtain, okay? That's what a probability distribution is. What are all the possible probabilities, okay, from the possible outcomes that I get? The random variable is what you are actually trying to measure. So what property are you trying to measure, okay, or what attribute? So if you have a die, okay, the property or the attribute that you're trying to measure is, what side, okay, of the die does it fall on? 1, 2, so on. If you're flipping a coin, then what is, okay, the side of the coin that it falls on? That would have been your random variable. You can have other random variables, all right? Now, the key thing is that each outcome, okay, will have one single value. So a heads, okay, is going to have a single value associated with it, and then you can find what that probability is. And then it can be either discrete or it can be continuous. So I want to give you a few examples with this discrete or continuous, for instance. Okay, so maybe I'll put up another page in here. All right, let's try to go that way. And then I'm going to write this out for you. So here are some examples, and you can kind of think back, are these discrete random variables or are they continuous? So let's say, you know, you were trying to measure the number of, let's say, goals scored in a game. Okay, so maybe in a soccer game or something. So is this discrete, okay, or is this continuous? Well, the number of goals that are possible, you either will score 0 goals, 1, 2, 3, okay, and so on. So is this discrete or is this continuous? It's discrete, okay? Between 0 and 1, there are no values at all, okay? So, and so on, between 1 and 2. So they're basically kind of like digital, like discrete points in time. Now, here's another one. What if instead, maybe you were measuring the time, okay, of, let's say, completing your homework, okay, of completing, okay, your homework. Well, time is continuous. Now, we could make it discrete where we're saying, you know, we're only counting minutes, you know, so it takes us 1 minute, 2 minutes, 3 minutes, so we're rounding. But as you know, time, okay, is a continuous flow. So if we had, assuming we had, you know, if we were capable of measuring, okay, all the, so not only minutes, but seconds and milliseconds, and we just kept going, so there's an infinite number of decimals, that becomes now continuous. So, you know, you can say, you know, between, let's say, 0 and 1 hour, right? Let's say that was the maximum. Okay, you can do your homework anywhere and your value can fall anywhere in between there. Now that is continuous. And that, now if we were drawing a probability distribution of this, you know, so for how long this would take, then we would have a nice, you know, graph in between 0 and 1 hour that would flow. While if we were trying to graph this, okay, and the probabilities of scoring, you know, 0 goals, probability of scoring 1 goal, then it would still be just points in terms of that distribution that you would have. Okay, so here's, you know, another example. So the result, let's say, you know, of flipping a coin, we knew, okay, was discrete. Of rolling the dice was also discrete. But what if, you know, we were measuring, let's say, some pressure, all right, okay, in bodily fluids. Okay, bodily fluids, maybe like blood pressure or something like that. So now, again, depending on what you have, maybe the pressure is being rounded, so it might become discrete because you're rounding it through. But the pressure itself, okay, in terms of measuring, so that quantity of pressure would actually be continuous, all right, because of the fact that pressure, let's say if it was between 0 and who knows what we're measuring this in, let's say maybe, you know, 200 millimeters of mercury, let's say if it was blood pressure or something like that. So we would need a unit here, and it could fall anywhere in between here. Okay, because as you know, you can possibly get a pressure reading of 80 point, you can have an infinite number of decimals. If you're in healthcare, you most likely would round this, okay? So then it becomes discrete, but if you weren't rounding, then we could do a probability distribution, okay? That is for continuous random variable. So here's the, pressure in bodily fluid. That is your actual random variable that we're trying to measure out. And then the possible outcomes for it, the probabilities, we could map out, okay? Now, as I said, we'll try to concentrate on the discrete because that's what you typically do in your, grade 12 probabilities. But you may get into continuous, if you ever study later on, some of these. So what else, did we have on our agenda on this? The uniform probability distribution I mentioned, expected value. This one is actually really kind of important to be able to know and calculate. So I'm going to just show you what this expected value is. And you can think back, okay, and when you were studying averages, okay, but now we have a weighted average. So our random variable, I'm going to come back to this die, all right? Okay, and I'll try to show you through that. So we have our expected value, all right, for that distribution that we would carry. If you're thinking back of weighted averages, how did weighted averages work? Weighted averages, okay, work that we would take the weight, we would multiply it by the outcome, and we would sum up the total of the weighted, okay, outcomes. And then we would divide by the sum of all the weights. All right, that's what a weighted average was. Now the expected value is exactly the same thing. Now, so I want to, you'll see that this division will disappear. The weights are the probabilities. All right, so it is the probability. So let's say, the probability, okay, of obtaining, say, the first outcome. So I'm going to call that x1. So it could be 1 if we're rolling a die. And then we multiply it by the outcome itself. Okay, so x1 plus, all right, this is going to be continuing. So probability of x2 multiplied by, the second outcome. And we continue this all the way. Now we're assuming that it's discrete. All right. Okay, so we can just add them up. So this we would continue. I'm going to do this a little bit longer. So this would continue all the way until you multiply all your probabilities times the actual outcome. So that variable itself, I'm going to call this n. And then at the bottom, okay, we have to add up all the weights, which are our probabilities. However, what do we know when we sum up all the probabilities? This entire thing is just equal to 1. So it disappears. And it turns out that our expected value, I'm going to duplicate it, just becomes this because we're dividing by 1. And it is very often written in our sigma. So sigma, this is kind of the notation, which is the summation notation of, okay, whatever the probability is multiplied by your outcome. Okay, and then this would have been from I equals to 1, okay, all the way up to n. So it just simply counts all of them up. So again, coming back to the die, well, it's uniform probabilities, right? So what would we have? Well, the expected value for this, so the expected value would have been, okay, so this is, what is the probability? Well, the probability is 1 over 6. This is the probability of obtaining times 1 plus 1 over 6, okay, times, okay, obtaining 2 plus, okay, and this continues on, right? So 1 over 6 times 3 plus 1 over 6 times 4, 1 over 6 times 5, and then 1 over 6 times 6. So that's the expected value, or what is the average? Expected value, what's the expectation that you would have in all of these? Well, you notice that you have 1 over 6, so that's uniform. I can actually factor that out. So this is going to be 1 plus 2 plus 3, plus 4 plus 5 plus 6. All right. Okay. And this is what we have in there. And so that expected value, and you can now just count all of these up. So 1 plus 2, which is 3, 6, 10, 15, 21. So it would have been 21 over 6. All right. So that is the expected value that I would have, right? Assuming that I've actually counted this up correctly. So now that expectation is basically just the average overall that you would obtain. All right. Now, this, okay, in general, so calculating this expected value can have numerous results, okay? So sometimes it has a great meaning, sometimes it doesn't have a meaning at all. And I mean, this, we have a uniform distribution. So, you know, the expectation is, I mean, they're all equal probable in terms of rolling a die, but those expectations, okay, do have some meanings. So I want to end this off, right, with one nice example, which is common. So I'm going to show you what the example is, and then we'll wrap up, okay, this particular video. Okay, so let's try to illustrate this through this example. So I'm going to take, you know, all the different items and try to illustrate this to you. So we have a lottery has sold 2.5 million tickets. So in total, there are 15 tickets that hold a price. The highest single price is 1 million. There are also 4 50,000 prizes, and then 10 2,000 prizes. So we have 1 million, you know, 4, so that's 5, and then 10, okay, of the 2K, so that's 15. So part A says, what is the probability of winning the highest prize? So that's not hard to answer. So the probability of winning 1 million. Well, there's only one single ticket that is sold, so it's tiny. All right, so this is what we have there. Now, if it asked us, you know, what's the probability of winning, let's say, a ticket, you know, of winning some prize, then, you know, we have 15 of those that actually hold something, so we would have had that. Okay, now part B asks us, construct a graph of the probability distribution for this lottery. Okay. Well, first of all, we actually need to figure out what the random variable is. So random means that, well, we're going to be picking at random any tickets, right, that we would have. And now what we can say is the following. We can say that a random variable is going to be, okay, so the outcome is what price, okay, is attached to the ticket. Well, if it is the price that we're looking for the outcome, well, there's only 4 possible outcomes. You can have the outcome of not making any money, right? Which is going to be almost everybody. You can have an outcome of receiving $2,000. You can have an outcome of receiving $50,000. Or you can have an outcome of receiving the biggest prize, which is 1 million. So this is a discrete random variable, right? So at random, we can choose people, and most of them will not get anything, but there's going to be some that are going to be winning a prize. And now what we want is we want to be able to find our probability distribution. So what is the probability of getting no money, getting $2,000, $50,000, or 1 million? So I'm going to kind of graph this out, right? So it's not going to be very accurate just because of the numbers that we are dealing with. Actually, hold on a second. This is going to be a little tricky because, so I'm going to say stop here. I'm going to map the $0 here. I'm not going to put it right at the kind of, normally as we put it at the cross there at the origin. So I'll shift it over. Okay, so we have 0, right? So then it continues on. Now I have to do kind of something like this to break. Well, that's not what I wanted. Okay, so I'll do that. Okay, break it. Let's say, so this is winning $2,000. Right, so that little line just means, because between 0 and 2,000, obviously there's a lot of numbers. And now between 2,000 and 50,000, there's obviously also a lot of numbers there. Okay, I will make this super neat. This is 50K. And it's going to be 1 million. 1 million. So that's my X. So these are my 4 possible outcomes. And now what are the probabilities? So, well, I mean, the probabilities, you know, if I keep them, okay, so probability of winning nothing, Okay, so there's 15 prizes in total. So this is going to be 2, 4, 9, 9, 9, 8, 5, all over 2, 5, 0, 0, 0, 0, 0. Okay, so that obviously, I don't know, this is almost 1. Okay, so it's going to be practically there, right? I'll just put it like this. I hope that you see it. And now the rest is going to be puny. So the probability of 2,000, I think there was 10 of those, 10. So this is going to be 10 all over 2, 5, 0, 0, 1, 2, 3. I mean, you know, it's going to be somewhere, you know, within here. Even lower, right? So we would actually probably have to, you know, map these on. Then we would have probability of 50,000, which is even less. There's 4 of those. So 2, 5, 0, 0, 1, 2, 3, you know, so it's going to be even lower. And then this one's going to be 1 over, you know, as we put it here, 1 over 2.5 million. So as you can see that, you know, the distribution, it's all pretty much stuck at 0. Nobody wins. And then there's a few happy campers there on the other side. All right, so that would have been the probability distribution, okay, of that. So I hope that actually shows you know, what that random variable is. We mapped it to the price of money, and then we can find the probabilities, and then we can show the entire distribution across. Now it says, what is the expected profit that the lottery would make if each ticket was selling for $5? This is really good because it now forces you to think about expected value. Okay, so what's the expected profit? So in total, you know, they're paying out money. For most tickets, they're not going to pay out anything. But for these, they do have to, and then they have to pay out one big sum. So this actually, so this part C, what we have to do is we know that we are receiving $5 per ticket, right? But that's not our profit because we still have to pay out. So what's the expected payout? So I'm going to put the expected value in here. All right. So that's now why the expected value is kind of important because it has a meaning. It will actually tell us what the expected payout is for all of these tickets. So we have, so the probability, so this first one, right? It's going, I'm going to write it out just so that you can see this whole thing in action. So the probability is, what's the probability times the outcome, right? So we have 2, 4, 9, 9, 9, 8, 5, all over 2.5 million. 1, 2, 3. But it is multiplied by 0, right? Because we're not paying anything out. So this is going to disappear. So for all of those tickets, we're not paying anything out. Now, plus, we are paying out for the 2,000. So that was 10 of those. So I have to say 10 all over 2, 5, 0, 0, 1, 2, 3 times, this is the $2,000, plus, now we're paying out 4 of the 50,000, and we're paying 1, okay, of the major prize, which is going to be the biggest payout. 1, 2, 3. Okay, now we can calculate what all of this is. So we're going to get a sum. And this sum means that that is how much we have to pay out. Okay, what's the expected value of our payout for each ticket? It's not 0. For most people, it will be 0, but it's the average, right? So let's take a look. I'm going to compute this in fast forward fashion, hopefully. Okay, so there we have it. So let's round this off, okay, to 49 cents, approximately. So this means that for every ticket, we're going to have to pay out this much. That's the expected payout. So that means our profit, because we're getting $5 for each ticket. Okay, so if we do this, so our profit is actually $4.51. Okay, maybe a little bit more for each ticket. So that's the profit that we are making if we're going to be selling those 2.5 million tickets. So this is where these probability distributions and probabilities in general, and in particular expected value, is kind of useful to be able to find out. It wasn't so useful for the dice, right, to find the expected value. We can still do it, but the meaning isn't really that relevant to us. But in here, the meaning is relevant based on what the outcome is. Okay, so that's the expected value. This is the expected profit that we would have. Okay, so what else? Do we have one last one? Okay, how many $2,000 prizes could the lottery afford to give out if it wants to have a $2 profit per ticket? Okay, this is super neat. So what we want is we want $2 profit. We currently have 4, so we can give out plenty more, okay, of those. So how would we set that up? Okay, so the setup will be the same. So I'm gonna avoid this because this just equals to 0. All right, so I'm gonna take all of this. Okay, I'm gonna copy this. Copy. That's the expected value, right? Okay, so that's what we're going to have there. Now, okay, we don't know, so I'm going to, call this, so unknown, how many of these will we have? I'll put N here. I don't know how many of these $2,000 ones that we will have. Now, what will this give us? This entire thing, so this, okay, what would this give us? Well, thinking back from the one above, it gives us how much we have to pay out for each ticket, right? So that's what we basically had. So this is the payout for each ticket. So in order to have a $2 profit, so $5 minus, the payout for each ticket, we're supposed to have $2. So clearly this payout, okay, is equal to $3. So we're solving this equation right here for N so that the payout is $3 and we're still left with a $2 profit. So that's how we would have to set this up. So, and you'll find out if you solve this, okay, you're gonna be able to actually give out quite a lot of these $2,000 ones to make people happy and still, come up with a $2 profit per each one. So I'll leave that for you. You can calculate it. You can put down in the comments, okay, below in order to calculate it. I'll just kind of provide you an answer in case you wanted to find out what it is, okay, and then I'll do the calculations in fast forward fashion, all right, and that's going to be it. All right, so there you go. Okay, so I set it up. I just multiplied both sides by 2.5 million. So that shifted that over. 4 times the 50,000 is 200,000. 1 times 1 million is that. We bring this over to the other side. Okay, we subtract and then we divide by this. And we have quite a lot of prizes. Okay, the $2,000 prizes. All right, so that is it for this video. Thanks for watching. Okay, we'll see you in a future one. Bye, everybody.